Welcome all to this session, which is going to focus on the general curvilinear motion. So basically, we are going to have a basic understanding of the curvilinear motion, but we are going to treat it or characterize it in different coordinate system in the later sessions. So the only objective of this session is to describe the motion of a particle traveling along a curved linear path. So let's just state some definitions. Curvilinear motion occurs when a particle moves along a curved path. Path is described in 3 dimensions. Sometimes motion happens in 2 dimensions, but it can happen also in 3-dimensional space. We will, as we did before, characterize the position, velocity, and acceleration in a vector notation in order to be able to describe the motion. Now, as far as application, pendulum, for example, represent a simple 2D curvilinear motion, because if you follow the path here, it's basically a curve. While in this car, for example, as it moves in this spiral kind of path, it represents a curvilinear motion in a 3-dimensional space. Now, as far as position, this is here to describe how the position of a particle is defined over a curved path. So basically what we have a particle B moving along a curved path. So since the motion is often 3-dimensional, vectors are used to describe it. So in here, for example, what we did, we will establish usually a coordinate system, and we take a point as the reference, like point O, and then we construct a position vector pointing toward the particle. The interesting part here is that the position vector itself is moving with the particle, so it's not fixed. As the particle, for example, move from one position to another. So S here is path function, while the path is basically the blue line, the blue curved line. Now, so as we discussed in the previous slide, a particle moves along a curve defined by a path function S. Then the position of the particle measured from a fixed point O, which is this one, is given at any instant by a position vector R equals to RT, which means that the position vector itself is function of time. Now, displacement is measured by how much distance is traveled. So if the particle moves a distance delta S, as shown over here, along the curve during the time interval delta t, then the displacement is determined as delta R, which is equal to R prime minus R as a vector. So these vectors are shown here. So this is basically the position of the particle at point P, at a location P, and then it moved to point P prime. So as you see, the distance traveled is delta S, while the displacement, which is delta R, is shown over here. This is the displacement vector over here. So if we know the displacement, we can measure the velocity. So the velocity represents the rate of change in the position of a particle. Now, the average velocity of the particle during the time increment delta t is v average, which is going to be delta r over delta t. What is delta r? So if we write this one in a vector notation, then this is delta r over the time it takes the particle to move from point P all the way to point P prime. As we define the average velocity here, we are going to define the instantaneous velocity, which is basically the time derivative of the position. What is important to note is that the velocity vector over here is always tangent to the path of the motion. So this one is basically tangent to this path. And if we want to define the velocity, the instantaneous velocity, it is basically the limit when delta t approaches 0 for delta r over delta t, which is equals to dr over dt. So it's similar to what we did in the previous section. The magnitude of the velocity is called the speed, as we defined before. So since the arc length, which is here, delta s, approaches the magnitude of delta r as time goes to 0, the speed can be obtained by differentiating the path function, which means we can say that the speed is equals to ds over dt. The acceleration of a particle moving along a curved path is not different from that on a straight path, which is a rectilinear path. It is the rate of change of the velocity with respect to time. Now, so for example, if the particle P is at this position and then it moved to this position, which is P prime, and if we basically we're able to measure the velocity of this particle at this time. So this is the tangent. So be careful, as I explained before, velocity is always tangent to the path. And this is also how the second vector of the velocity v prime is tangent to the path. Then basically, if we take the delta v, which is represented down over here, we can take the origin over here, and this is v, and this is v prime, and then we can find delta v. If we do that, we can find the average acceleration. So the average acceleration is equals to dv over dt, which is equals to v prime minus v over dt. The instantaneous acceleration is the time derivative of the velocity. So if we want to find a as the instantaneous acceleration, then it is the limit as delta t goes to 0 for dv over dt, which is equals to dv over dt, which is equals to d2r over dt square. A plot of the locus points defined by the arrowheads of the velocity vector is called the hodograph. So let me repeat that again. So if we assume that there is a particle, this particle, of course, it is at this position, but before it was at this position, in the future it will go to here and there. So if we draw the velocity vector like this. So this is the velocity vector, and then we have this one over here. Later, we will have another velocity vector, and so on. Now, as you see, the arrow heads over there, this one, this one, this one, and this one. If we connect them with a path, then this path is called the hodograph. What is interesting about the hodograph is that the acceleration vector is indeed tangent to this hodograph at a point of time. So, but it is not tangent to the path function s. So it is, if this is the path s, we know that at a given point of time, velocity is tangent to it, but the acceleration may not be. The acceleration could be here as a vector, could be here, we don't know. Now, so the acceleration vector is usually directed toward the inside or the concave side of the curved path. And this is, as we're going to discuss later, because of the normal acceleration, which is always pointing to the center of the radius of curvature. So to summarize the key point of this session, we define the position vector, velocity, and acceleration for a curvilinear motion. We said that velocity is tangent to the path, and we said that the acceleration is tangent to the hodograph. That's it. Thanks a lot.